today you are going to be doing 2.2b. Good for you. Limits involving infinity, horizontal and oblique asymptotes. Alright, so first thing we're going to look at are the different end behavior rules based on what type of asymptote we have. And that's determined by the type of rational function we have. So, if the rational function that you're given is something that is bottom heavy, as in the degree of the denominator is higher than the degree of the numerator, that's going to give you a horizontal asymptote of y equals 0. So does everybody understand what I mean by bottom heavy? See how the degree in the denominator is 2, degree of the numerator is 1. You with me?
Yeah.
Okay. No, you're all good. Equal degree is where you have the same degree numerator, denominator, something like this. They're both degree 1. When that's the case, you divide the coefficient of the leading terms together to get the horizontal asymptote. So in this case, it would be like 4 divided by 2, which is y equals 2. And that horizontal asymptote determines where the function's going as it approaches positive and negative infinity. So do you see here, like for this one, as we approach positive infinity on the x, we're just getting closer and closer to 2. As we approach negative infinity, we're just getting closer and closer to the y value of 2. Everybody see what I'm saying by that?
Mm-hmm.
Okay. And then lastly, we have oblique asymptotes. So oblique asymptote is when you have a top-heavy function, okay? And with a top-heavy function, you end up with an oblique asymptote. Oblique asymptote can be a linear function, it could be quadratic, it could be cubic, it could be any degree function, but that function's end behavior determines the limit of the original function. So in this case, what kind of oblique asymptote do we have here? Is it quadratic?
Linear.
A linear function, the end behavior as we go to the negative infinity direction, our function goes to the negative infinity direction. As we go to the positive infinity direction, our function goes to the positive infinity direction. That determines the limit of the original function. The end behavior of the oblique asymptote determines the limit of the original function. Okay? Alright, so we're going to go ahead and do some together. We're going to do some of each type. So let's look at letter A first. So letter A, is it top heavy, bottom heavy, or equal?
Bottom heavy.
Good. So since it's bottom heavy, that means that our horizontal asymptote is what? Y equals 0. That means that our function, as we approach negative and positive infinity, the limit is also 0. Any questions about part A? Alright, part B, top heavy, bottom heavy, or equal? Equal. You see how the degree on the top and bottom are the same. So when that's the case, to find your horizontal asymptote, you take the coefficients of those two terms. So that's going to be 3 over 2, also known as 1.5. That is your horizontal asymptote, which means that your limit approaches that horizontal asymptote on the left and the right. So even if it was negative infinity here, the answer would still be the same. So does anyone have any questions about A or B? Those are the easier ones. Okay. Now we're going to go ahead and move into C. So is C top heavy, bottom heavy, or equal?
Top heavy.
Good. So since it's top heavy, we're going to have an oblique asymptote. So we know that oblique asymptotes are different types of functions. We have to determine what that function is. We can actually determine that function by using division. Remember long division from algebra 2? But luckily, if your denominator is a linear binomial, as in its first degree binomial, you can actually use synthetic division. Do you remember synthetic division at all? Well, I did it with you guys in algebra 2, so. Alright, so let's refresh your memory on synthetic division. So you draw this sideways L-shaped thing. Does that kind of ring a bell when you draw that? So, yes. You have a question? Are you just saying that it makes sense? And you're going to put these little, like, dashes here. Those are going to be where your number you're dividing goes and then where your remainder goes. Okay? So here's how you set it up. What you're dividing by, whatever that number is, the constant, you're going to take the opposite sign of that. -3. And then what goes inside is going to be the coefficients of these terms. Now the problem with this is, if you're missing any terms between any, you have to put those in as placeholders. So see how we go from x to the 4th all the way to x? We're missing what two exponents? 3 and 2. We have to put placeholders in for those, okay? So whatever your degree is, there should be one more number written in the inside. So if you have a degree 3, you should have 4. If you have a 4th degree, you should have 5. So the coefficient of x to the 4th, the coefficient of x to the 3rd, coefficient of x squared, because those are both missing, the coefficient of regular x, and then the coefficient of the x0, which is the constant. Now you bring down the first number, and you multiply this number by what's on the outside. Negative 3 times 3 is? Negative 9. Then you combine 0 minus 9 is?
Negative 9.
Negative 9. Negative 9 times negative 3?
27.
0 plus 27?
27.
Good. 27 times negative 3?
27 times negative 3,
Good. Negative 81 plus negative 1?
-82.
Good. And then the last one? Sebastian, what was it? 3 times negative, or 82? I forget, you said it earlier.
246.
6. Good. What's 246 plus 1?
240.
Good. So, one beneficial thing about finding oblique asymptotes is we actually don't care about the remainder at all. Not today. Now, here's how you find the oblique asymptote itself. These numbers represent the coefficients of the division terms, or what you get as the result. This is your constant, this is your x, x squared, x cubed, and then if it kept going, and so on, right? So it would be y equals 3x cubed minus 9x squared plus 27x minus 82. That is your oblique asymptote. So you're thinking, what's the point of this? So the point of this oblique asymptote is it tells us this end behavior of this oblique asymptote tells us what the limit is doing, okay? So this is where we reference the stuff from yesterday. Is this, what is this? Odd. Would you all agree that this is odd positive?
Mm-hmm.
So you look at this to determine if it's odd or even, this to determine if it's negative positive. Odd positive goes down and then up, right, from your end behavior rules. So on the left it's going down, on the right it's going up. This end behavior determines the limit of the original function. So as the limit approaches negative infinity, we're going, that's this way, so we're going down to negative infinity. So just a rule is if your division, if you deal with an oblique asymptote instead of a horizontal, your limit will always approach one of the infinities. Okay, oblique is going to give you an infinity limit. Does that make sense to everybody? Yes? No?
Mm-hmm.
Okay, that's how you do that. Alright, D, top heavy or bottom heavy?
Bottom.
Bottom heavy is y equals 0, so the limit as we approach infinity is 0. Okay, next one. Top heavy or bottom heavy? It's top heavy, and you could do synthetic division. However, can't this be factored on the numerator? What could I factor that numerator into?
X plus 9.
Good. So what that's going to result in is this is canceled out, and my limit of the function I'm actually taking the limit of is actually just x plus 3. Now, we all know from algebra that when we cancel out something in the top bottom, do you remember what that does to the function? It creates a hole in the function. But do we care about holes in calc with limits? No, because we don't care about if it exists at that point. We just care about if it's approaching. So in this case, we don't care about the holes. In algebra, we do in some cases, right?
Mm-hmm.
So now we're basically just taking the limit of the function as it approaches infinity of x plus 3. What kind of function is x plus 3?
Linear.
It's just a linear function, right? It looks like something like this. So you could draw it and just think through it, or you can use the rules of end behavior, right? Isn't this odd positive? So if it's odd positive, as it approaches positive infinity, it's going up to infinity as well. So you have options on that one. Now, had you done the synthetic division, you would have gotten this is your quote-unquote oblique asymptote, which would also have the same end behavior and have given you the same answer for the limit. Okay?
Mhm.
So that's it. I have your homework now, and you can work on that for the rest of the